Welcome to episode 15 of George's Random Astronomical Object. In each episode, I run a random number generator to select random astronomical coordinates in the sky, and I then search for an astronomical object near those coordinates and spend a few minutes talking about that object and what makes that object so interesting to astronomers. So I will now run the random number generator. The generator has blown out another light bulb. I'll need to switch over to LEDs. The coordinates from the random number generator point to a location in the constellation Taurus. That's Taurus the Bull, the same constellation associated with the zodiac. The specific coordinates are 5 hours, 10 minutes, 2.4 seconds right ascension, and plus 18 degrees, 0 minutes, 42 seconds declination. These are the coordinates for an object identified by its coordinates J0510 plus 1800. The J refers to the coordinate system, which was set up in the year 2000. The first 4 digits are the right ascension, and the second 4 coordinates are the declination. This galaxy, which is located at a distance of about 4.5 billion light years away, is a blazar, a type of galaxy with an active galactic nucleus, or AGN. What's surprising about this galaxy is that it might be something that I've worked with before in my research, but I'm not exactly certain. I'll explain in a few minutes. First, let me describe what an AGN and what a blazar are. An AGN consists of a supermassive black hole millions of times more massive than the Sun, a disk of gas and dust falling into that black hole, and jets of ionized gas that emerge from above and below the poles of the black hole through complex magnetohydrodynamic effects. The center of the disk can get very, very hot and will produce a broad range of electromagnetic radiation. When the disk is viewed from the side, we don't see the central region from Earth because it's hidden by all the gas and dust in the disk, but we still see the jets on either side of the disk. Because the jets produce very large amounts of radio waves, and because these types of AGN are usually identified by their radio emission from these jets, these objects are called radio galaxies. When we can see the top of the disk, although we may not be looking directly down the axis of the disk, we can also see into the really hot part of the center of the disk near the black hole, and so we will see a very bright point-like source in some or all parts of the electromagnetic spectrum. We very frequently see the jets as well, although they will appear to be moving closer to along our line of sight rather than sideways. These objects are called quasars because when astronomers first saw them, they thought they looked sort of like stars and called them quasi-stars, or quasars for short. Blazars are quasars where we are looking directly down the jet coming out of the top of the AGN, so they look exceptionally bright. I would be inclined to think that the word blazar combines the words blazing and quasar, but while researching this episode, I found a reference that seemed to indicate that the BL in blazar comes from BL Lacertae, the first object identified as a blazar. I was really disappointed too. So, J0510 plus 1800, like other blazars, emits a huge amount of radiation in all parts of the electromagnetic spectrum. However, the gamma radiation from J0510 plus 1800 attracts a lot of attention. On Earth, gamma rays are extremely rare. They're produced mostly by nuclear bombs, although a few gamma rays can be potentially produced by lightning and by some radioactive decay processes. Comic books about the Hulk and other Marvel comic book characters who got their powers from gamma radiation are actually much more common than the gamma rays themselves. In space, gamma rays are also very rare. Any object that produces gamma radiation will receive a lot of attention, and that includes J0510 plus 1800. The gamma rays from this blazar, as well as other blazars, come from electrons oscillating within magnetic fields near the base of the jets in the AGN. The electrons are moving towards us at close to the speed of light, which causes the radiation to be Doppler shifted and boosts the amount of gamma radiation that we see from these blazars. The gamma radiation from blazars in general, and J0510 plus 1800 specifically, is also very variable. Gamma radiation flares are observed very frequently from these objects. Astronomers have been monitoring many blazars, including J0510 plus 1800, with the Fermi Gamma Ray Space Telescope, so they can see these flares when they happen. Since this radiation comes from the base of the jets, it can potentially be used to understand the environments near the supermassive black holes in AGN, although it still seems like people are trying to work out exactly what the heck is happening in these locations. Despite the variability of J0510 plus 1800, particularly in gamma rays, people working with the Atacama Large Millimeter/Submillimeter Array, or ALMA, have decided to use it as a calibration source. Now, it sounds sort of weird to take something really variable and use it for calibration, but this actually makes a lot of logical sense, and I'll explain. So, ALMA is a telescope in Chile consisting of 66 antennas, which, as you can gather from its name, observes millimeter and submillimeter radiation, which is on the opposite side of the electromagnetic spectrum from the gamma rays. ALMA works as an interferometer, which means that astronomers do not record the signals from the 66 individual antennas by themselves, but instead record the signals from various pairs of antennas within the array. The waves of radiation will reach the different antennas at different times, and either the waves could be in phase, which will lead to the creation of bigger waves in a process called constructive interference, or they could be out of phase, which would lead to the waves canceling out in a process called destructive interference. While gamma radiation is rare, millimeter and submillimeter radiation is very common. On Earth, the type of thermal radiation that people normally associate with infrared light is also produced at millimeter and submillimeter wavelengths by just about everything. So right now, you are producing millimeter and submillimeter radiation, and everything around you is also producing that radiation. In space, the primary sources of this radiation are interstellar dust and ionized interstellar gas. Molecules both in space and on Earth also produce a lot of millimeter and submillimeter radiation. On Earth, the most common molecule that produces this type of radiation, or at least as far as I know, is water. In space, the most common molecule that produces this type of radiation is carbon monoxide. In any case, astronomers using ALMA, which includes me because my day job is to help other astronomers using ALMA, need a way to calibrate their data so that they know exactly how much energy they are measuring from their astronomical objects. This is called flux calibration. Surprisingly, the best objects to do this are a myriad of solar system objects, which includes Mars, all of the gas giants, a few of the largest moons of the gas giants, and a couple of the largest asteroids. These types of objects mainly reflect sunlight, but at millimeter and submillimeter wavelengths, they emit thermal radiation that's really easy to model. The solar system objects are also really bright at submillimeter and millimeter wavelengths, which makes it easy to detect those objects and to accurately measure the radiation from them. However, solar system objects have two drawbacks as calibration sources for ALMA. First, as you would expect, they move around a lot, and sometimes there aren't any convenient solar system objects around in the sky that can be used for flux calibrating and observation. Second, ALMA is not designed to measure emission from objects as large as the larger planets, moons, and asteroids in our solar system. Strangely enough, it's possible to place two ALMA antennas at a certain distance where the combination of the size of the planets and the effects of interferometry lead to the planets looking invisible to the telescope. To solve these problems, support scientists organized the system for the flux calibration of ALMA that did not require observing solar system objects for every set of science observations. The scientists identified about 40 AGN that looked very bright and very point-like at millimeter and submillimeter wavelengths. This set of objects, which are evenly spaced around the sky, are called grid sources by ALMA, and J0510 plus 1800 is one of these grid sources. Once every 2 weeks, ALMA observes these grid sources along with a solar system object using a subset of antennas which are spaced close enough together that the solar system object does not magically disappear. This allows ALMA scientists to calibrate the brightness of the grid sources. Then, when the observations for a science program are performed, a grid source can be observed for flux calibrating the data for the other objects. By observing the grid sources frequently, ALMA scientists are able to track the variability in these objects, including J0510 plus 1800, which makes it possible to use these sources for flux calibration even though they're variable. As I mentioned before, I work as an ALMA support scientist, and I've processed a lot of ALMA data. This means that I've looked at lots and lots of flux calibration data, as well as quite a few images of flux calibration sources. It's quite possible that I've either used J0510 plus 1800 to calibrate ALMA data, or I've made images of J0510 plus 1800, or I have inspected images of J0510 plus 1800 created by the ALMA data processing pipeline to ensure that it worked properly. However, these calibration sources have names that just aren't really easy for me to memorize, so I don't really remember whether I worked with a source or not. It would be cool if I did. Well, in any case, that's my description of J0510 plus 1800, and the location on the Earth's surface corresponding to the position of J0510 plus 1800 in the sky is located outside of the village of Dadapur in India. If you look at maps, you'll see that nearby this location are the Naranja sugar factory and a temple to the Hindu god Hanuman. Hanuman is a monkey god associated with Rama, and Rama himself is an incarnation of the god Vishnu. The website for this podcast is www.randomastronomicalobjects.com, which you can visit to download episodes of the show, read information about the astronomical objects, view images of those astronomical objects, and send me random feedback. The audio was recorded and edited by George Bendo. The music is Immersion by Sasha Endy at www.sasha-endy.de, which is distributed by filmmusic.io under a CC 4.0 attribution license. The sound effects are from the Freesound project at www.freesound.org. Thanks for listening.